Hello and welcome back. We're looking at Chapter 3, Part 3, Slide 30 for our Chemistry for Engineers class. And so we're picking up with Slide 30 and we'll go ahead and finish off the lectures now. Okay, so this is a big practice problem, and it tells us that we are making this feedstock molecule from biomass, and it's 2-propanol, and here is the formula. Okay, and it tells us that we have 423 moles of the compound. Okay, and how many kilograms can be made? Okay, so let's take a look. So in this, we have a series of steps. And our first step here is to find the molar mass of 2-propanol. Okay, so we have 3 carbons, so that's 3 times 12.011 plus, now see how we have the 7 and another hydrogen, so we have 8 hydrogens, so 8 times 1.008. And now we only have 1 oxygen, so plus 15.999. And if you're wondering where we got this, again, just to review, 12.011 is the molar mass of carbon from your periodic table. 1.008 is the molar mass of hydrogen from your periodic table, and 15.999 is the molar mass of oxygen from your periodic table. All right. So again, it's great for you to pause this video and see how much of this you can work through on your own, as you would do if we were in class. All right. So when we work this through, what we end up getting here is 60.096 grams per mole. And that's our molar mass. And now we have step 2 says convert from moles to grams. So here we take our given value here that we have for our moles, and that's 423 moles. And now, because we need to cancel this out, we have 1 mole on the bottom, and that cancels out our moles, and our molar mass here goes on the top, 60.096 grams, because that's what that means, grams in a single mole. Okay. So now for our grams here, and we can have, it says 3 significant figures. So usually what I do is, here, I'll show you. Okay, so we have 25,420.6 is the answer that we get here. And since we can have here we have 1, 2, 3 in our 423. So we can have 1, 2, 3 in our significant figures here. And so what that means is that we have 25,400 grams to make. Okay, that's a lot to calculate. So now why don't we come down here and we're going to convert from grams to kilograms. And we have 25,400 grams. And remember that there are 1,000 grams in a kilogram. And that is from chapter 1. And so because you have grams here on the top, we need to put our 1,000 grams on the bottom. And that means that we are dividing 25,400 by 1,000. And for our final answer, we are getting 25.4 kilograms. Okay. Okay, so now we have mass percent. So real quick, I'm going to go ahead and insert something here where we just review mass percent. So mass percent in a compound, it looks like this. Okay, so when we're talking about mass percent, the mass percent in a compound is equal to the mass of the element divided by the total mass of the compound. And then it's a percent, so make sure that you remember to convert that into a percentage. Okay, so now let's take a look at, for example, that propanol, that 2-propanol that we had before. So remember it was C3H7OH. And in our previous slide, we had found a molar mass of that of 60.096 grams per mole. And so if we wanted to find the mass percent of each element, so first of all, the mass of carbon in this, we've got 3, it would be 3 times 12.011 from our divided by 60.096. I need to grab a calculator. Okay. Have my calculator now. Okay. And so what this means, so we say 3 times 12.011 divided by 60.096. And also we're going to turn that into a percentage. And this means that we have 59.96% carbon. Now let's look at the mass. Oh, and that's mass percent carbon. Now let's look at the mass percent of hydrogen. So now the mass percent of hydrogen, we have 8 hydrogens. So it's the mass of the hydrogen divided by our total, which is 60.096 times 100%. Okay. And so now we have that 8 times 1.008, and then divide it by 60.096 and turn it into a percent, and we get 13.42% hydrogen. And then we can also find the mass percent of our oxygen. And we only have 1 oxygen here. Actually, you know what I'm going to do? I'm going to put little dividers in here. All right. So we'll divide that. And then and then divide that as well. That way, it was looking like it was very difficult to see. And coming back to this. Now, we only have 1 oxygen, so we'll just have one of them, 15.999, divided by our 60.096 times 100%. And that will equal and that will give us 26.62% oxygen. Okay. Now, this is really important because we can use something called a mass spectrometer, and it's going to give us these percentages. So then what we're going to do is sometimes we'll take an unknown, we'll put it into a mass spec, and we'll get these percentages, and we need to work back from these percentages back to our empirical formula here. Okay, so you can do this with molar masses, but you could also do it with portions of it. Okay, so if you only had, say, 5 grams of this, then 59.96% of those 5 grams are carbon. Okay, so you can kind of go back and forth with that. All right, so let's take a look at going backwards now. All right. So first of all, when we're doing this, these are the steps that we're going to be following. We're going to assume a 100-gram sample size. the percentage element will be multiplied by the sample size equals the mass of each compound. So if you have 16% carbon, we'll say that we have 16 grams of carbon. And you'll see all these steps coming before. We're going to convert mass of each element to moles using the molar mass. Then we are going to divide by the smallest number of moles to get the mole to mole ratio for the empirical formula. And when division by the smallest number of moles results in small ratio rational fractions, we're going to multiply those by an integer to get whole numbers. So let's go ahead and just say in here we have step one is kind of these first two things. And we'll say, well, sure, that's step one. And then this is step two. Those will go together. And then here we'll have step three and step four. Okay. And step five if we need it. Okay. So go ahead and label those by the steps on your notes template. And we will go on and actually do some of this work. So now we're going to take this. We have nitroaniline, and we know from this problem that it contains 52.17% carbon and 4.38% hydrogen and 20.28% nitrogen and 23.17% oxygen. And we want to know the empirical formula. Okay, so let's go ahead and begin like this. So first of all, we have our step 1 and 2 from the other slide. And that is going to mean that what we're going to do here is we're going to say then that we have 52.17 grams of carbon. We have 4.38 grams of hydrogen. We have 20.28 grams of nitrogen, and we have 23.17 grams of oxygen. Now, the really important thing is sometimes you will not be given one of these. And so the thing to remember in that case, if you are not given one of these, is that they all will add to 100. Okay, so if you're not given one of these pieces, just remember that they will add to 100. Okay. Now our step 3 in here is to divide by the molar mass in order to find the number of moles. So that means for carbon that we're dividing by 12.011. And for hydrogen, we're dividing by 1.008. And again, I'm getting these from the periodic table. For nitrogen, we're going to divide by 14.007. And for oxygen, we're going to divide by 15.99. And if you're wondering why I can do that so quickly, it's because I have probably half the periodic table memorized by now. So you would need to basically be taking your periodic table and you would have to look each one of these up until you too have half the periodic table memorized. And most of you will by the end of the course. Okay, so that's our step 3. And that gives us 4.344 moles carbon and 4.345 moles of hydrogen and 1.448 moles of nitrogen and 1.448 moles of oxygen. Okay, so now we need our step 4. Okay, and step 4 here says to take the smallest one. Okay, so we have 2 here that are 1.448 and multiply everything by whatever is the smallest. Okay, so that means that we'll have 1 nitrogen and 1 oxygen, because that's just you're multiplying by the same thing. And then we get that 4.344 divided by 1.448. And now what we're doing is we're pretty much going to sort of round these like so. Okay. And so that becomes 3 carbons and 3 hydrogen. Say hydrogen, right carbon. Okay, try that again. Hydrogen. Okay. Now we come here to our step 5. And that is to place these values as subscripts. So we have C3, H3, NO. Okay. And that is our empirical formula. Okay. Now, in this case, we don't need to go on and do our next step in there. I guess this was a continuation. I'm just looking on my notes. I think this was a continuation of step 4. There we go. Great. So now let's take a look at one. So sometimes you'll need to do step 5. In this case, we did not. All right, now we have another practice problem here. This one's going to be a little different. We have 70%, okay, just taking a look at what we got here. All right, so it tells us that we have 70.8 mole percent palladium and 29.2 mole percent nickel. Okay, so the way we do this problem is a little bit different. Okay, so that means we're going to do it very similarly, but instead of starting with grams, we're going to be starting with moles. So again, the first thing that we're going to do here is we're going to assume percents as moles in this case instead of mass. Okay, before we had weight percent, now we've got mole percent. So that means that we're going to say, okay, that I have 70.8 moles and palladium is PD and 29.2 moles of nickel, Ni. Okay, now for our next step here is we're going to multiply by our molar mass instead of dividing like we did before. Okay, so that means that here the molar mass of palladium is 106.42. So we're going to multiply by that to get 7,535 grams of palladium. Okay, and we're not going to do significant figures until the end. That's very important. Okay, and nickel is 58.693 grams per mole. And so we're going to multiply that by nickel for nickel, and we will end up getting 1,714 grams of nickel. Okay. Now, now our next step here is going to be to add these together to get a total mass because we're looking for a weight percent. And here, this is the same thing as saying a mass percent. So we're kind of working our way backwards now at this point from what we had before. Okay, so we're going to add these. And when we add these together, we get 9,249 grams. And this is the total mass. Okay. Now remember that extra slide that I kind of snuck in there, talking about mass percent. Well, mass percent now is done in the exact same way, except that we aren't working with molar masses now. We're working with what we have here. Okay. So to find the mass percent of our palladium, we take the mass of our palladium, 7,535, and divide it by our total mass, 9,249. And we're going to turn that into a percent. And now you can see that we can only have 3 significant figures. So this becomes 81.5% palladium. Okay. And now we can also find our mass percent of nickel. Okay. And that's going to be the mass of nickel, 1,714 grams, divided by our total mass, and turned into a percent. Okay. For 18.5% nickel. Okay. So this is kind of like what we did in the last one, but backwards. All right, just a couple more concepts. Okay, so now what we're going to be doing is we're going to be looking at molarity. Molarity is the number of moles of solute per unit solution. Okay, so we would say capital M molarity is moles solute over your volume in liters. Okay, so you can turn this around too. You can say, okay, well, that means that moles equal molarity times volume in liters, and that your volume in liters is equal to your moles divided by your molarity. Okay. All right, so now let's take a look at this. A solution is prepared by dissolving 45 grams of NaClO. So this is sodium hypochlorite. I'm just going to go ahead and actually put that in there just for a little review here. So that is Na plus and ClO minus. And if we were to name that, then that would be sodium hypochlorite. Don't forget that because we're going to need to keep doing that. We don't do it a lot in this chapter, but in chapter 4, you're going to be doing lots and lots of naming again. Okay. All right. So first of all, it says to find the molar mass of the solute. Okay. So if we have NaClO, that means that we have one sodium and one chlorine and one oxygen. Okay. And so grabbing my periodic table because I actually don't have all of this already calculated. Okay. So that means that I have 22.990 plus the mass of chlorine, which I have here at 35.45, plus the mass of oxygen at 15.999. Okay. And that gives me a molar mass of 74.439 grams per mole. Okay. Now, my step 2 here says to find the moles of solute. And so I'm going to start then by using this mass right here, 45.0 grams. And when we go from grams to moles, then we put our grams, our molar mass here kind of upside down. So we have 74.439 grams per 1 mole. And we find that by dividing 45 divided by 74.439, which will give us 0.605 moles of our solute, which is NaClO. Okay. Now, our next step in here is that we need to convert our volume to liters. So remember that there are 1,000 milliliters in 1 liter. So our 750 milliliters, okay, and then we're going to be dividing that by 1,000. Okay, will get us 0.750 liters. And you know what I'm going to do? I am going to, I kind of want this to be a specific thing. So I'm going to add a decimal point right there. And you can too. You wouldn't normally do that in a problem, but that way we'll have 3 significant figures off of that one as well. Okay. Now, last, we're going to be solving for molarity. And remember, molarity is equal to moles divided by liters, or our volume in liters, sometimes people will say. Okay, so that means that we have 0.605 divided by 0.750. And now that I've given both of them three significant figures, that becomes 0.807. And just as a little review there, that is because our leading zeros don't count, and we only have those three significant figures. And the units for that is a capital M for molar. So we would say 0.807 molar. And there I have a little bit more there. Okay. All right, now let's go ahead and work our way backwards. And in this situation, we have 3.21 liters. Okay, so that's our volume in liters of 0.037 molar KNO3. And what we want to know here, our final question, is how many grams of solute are we looking for? So we're looking for a mass. So beginning here, let's start with solving for moles. So when we're working this out, remember that when we're using that molarity is equal to moles per liter or per volume in liters, that means that our moles are equal to the molarity times our volume in liters. Okay. And so in this case, our moles equal 3.21 liters times 0.037 molar. And that will give us 0.11877 moles. I'm only going to be able to have, at the very end of this problem, I am only going to be able to have 2 significant figures. And I will adjust for that later. It's better to adjust for sig figs at the end. Okay, so next is to find the molar mass of our KNO3. So KNO3 here means that we have 1 potassium and 1 nitrogen and 3 oxygens. Okay, so our potassium here is 39.098, and our nitrogen is 14.007. And our oxygens are 3 times 15.999. Okay, and when we work through that, we will get a molar mass of 101.102, and it's grams per mole. Again, don't forget to be pausing the video and seeing that you're getting the same values that I'm getting, because it's really important that you're really good at using your calculator for tests. Okay, so next we have here convert from moles to grams. Okay, so we take our number of moles, or 0.11877 moles. Okay, and because we're converting to grams, we're going to put this in here, 101.102 grams per every mole. And that's so that we can cancel out those moles. Okay, and I get 12.00788. Now I can only have 2 significant figures, so this just becomes 12 grams. Okay. All right. Just a couple more slides here. We're going to take a look next at dilution. Now, dilution is the process where we're adding a solvent to a solution to decrease the concentration of a solute. So you start with something that's really concentrated, and then you add some water to it, or some other solvent, and then it's less concentrated, or it's dilute. The thing to remember is that the number of moles of solute is the same before and after the dilution, because we've only changed the quantity of solvent. We haven't changed the quantity of solute. Okay, so since the number of moles of solute equals the product of molarity and volume, we can write the following equation, M1V1 equal to M2V2. All right, now because you guys are engineers and math is your thing, let's go ahead and take a look at how that works out. Okay, so molarity equals moles over your volume. Okay, so that means that your hang on a second. Okay, so moles before equals your first molarity times your second molarity. Now, your moles after, they haven't changed. So that means that your final molarity times your final volume have to equal your moles after. And because these are the same, we can set this up for each other. Okay. And this, and now we'll actually use this in multiple places, interestingly. Okay. So let's take a look at a problem and then we will be done. Okay, so this tells us that a chemist requires 1.5 molar hydrochloric acid. So see how it says that we require this? That means that this is going to be our final quantity. So this is going to be M2. Okay. Now, the only solution available is this other one, and it is a 6 molar hydrochloric acid. Is pretty concentrated there. Okay. And it says what volume of 6 molar hydrochloric acid? Okay. So that means that this is our first molarity. And it says what volume? So we're looking for V1. And what we need 5 liters of our 1.5. So that means that that's V2. Okay, so let's go ahead and list these out. So we have here that M1 equals 6 molar. Okay, V1 is what we're looking for. M2 equals 1.5 molar. And V2 is the volume that we need, or 5.0 liters. Okay. So now we go ahead and we set this up. And we're using that M1 V1 is equal to M2 V2. So we have 6 times V1 is equal to 1.5 times 5. And we can solve for V1 by doing 1.5 times 5 divided by 6. And that means that our V1 value will be 1.25 liters. Okay, now the question is, how will we make this? Okay, so we'll say to make this solution, we will take 1.25 liters of stock solution. And we need a total of 5 liters here, which means that we will add 3.75 liters of water. And this will make 5 liters of 1.5 molar HCl. All right. Thank you all very much. I will see you in class.